Today we will talk about insulators or dielectrics. Now, many of the properties of dielectrics such as electric polarization, dispersion and absorption of electromagnetic radiation by insulating materials, dielectric laws, dielectric breakdown, ferroelectric phase transition, piezoelectricity, etc., can be explained almost without reference to the atomic and molecular properties. From the point of view of practical applications, the insulators or dielectrics constitute an important class of condensed matter. The connection between dielectric and optical behavior, as we will see, of such electrically insulating materials also makes them interesting from the point of view of modern areas such as nonlinear optics, which is a particularly important modern topic of considerable theoretical and practical importance. Dielectrics comprise systems in which atoms and molecules have closed or nearly closed shell structure for electrons, and therefore they represent another extreme limit of electronic structure in contrast with metals in which conduction electrons are free. The electrons in dielectric materials are tightly bound to the atomic cores and are only slightly displaced from their equilibrium configuration by applied electric fields of moderate strength. This is even more true of the ions, and these small displacements are adequately described by a linear response theory in which the linear response theory assumes that the electric dipole moment which results from the application of an electric field of moderate strength is proportional to the strength of the electric field. Therefore, if P is the electric dipole moment, we can write P equals epsilon naught alpha E. Now, here E is the electric field, P is the electric dipole moment, and alpha is the constant of proportionality known as the polarizability. Of the atom or molecule. That is a constant which is measured in units of epsilon naught, the permittivity of free space. So, this P is the induced dipole moment, induced by the applied electric field. So, the dielectric polarization, this is the individual dipole moment induced per atom or molecule. Dielectric polarization capital P is the vector sum of the individual dipole moments, sum of individual dipole moments, and is usually defined per unit volume of the material. So, if there are n such atoms or molecules, n atoms or molecules per meter cube. So, from and then this polarization is also related to the applied electric field via the so called electric susceptibility. Therefore, combining these relations we get immediately chi there is another important vector called the displacement. D, which is defined by D equals epsilon naught E plus P. Therefore, plugging our epsilon naught E plus P is epsilon naught n alpha E. Therefore, I have epsilon naught times 1 plus n alpha times E, and this is usually defined as epsilon naught epsilon r E, where epsilon r is the relative dielectric constant. So, that we arrive at epsilon r equal to 1 plus n alpha, and we also know that P is chi e epsilon naught chi e. Therefore, we can write here epsilon naught chi e 1 plus chi e times E. So, comparing this and this, we also get 1 plus chi e. Therefore, we get chi e equal to epsilon r minus 1. Of course, this is a relation which is valid only in gases. In which case we assume that the field that we are applying here is the same as the field seen by the atom or molecule. This assumption is not valid in condensed matter. Such as liquids and solids. So, this relationship between the electric susceptibility and the relative dielectric constant via this, so chi e is also equal to n alpha. So, this has been verified to a great extent in many gaseous dielectrics, but in a condensed material like a solid dielectric, this assumption, this relation is not valid. This is known as the Clausius relation. This is not valid because the dipoles which are present, the atomic or molecular dipoles, interact among themselves. There are dipole-dipole interactions which produce internal electric fields, so that the local electric field seen by a solid atom or a liquid atom or molecule is different from the field which is actually applied. So, this local field differs. So, E local is not equal to E applied. That is the reason why this relationship is not valid. How does it differ? Now, the local electric field has two contributions. Let us look at the process of polarization a little carefully. So, I have an atom in which there is an electronic cloud, uniform charge density of electrons, and there is a central nucleus. Now, this is a spherical atom, we are assuming it to be spherical to keep the discussion simple, is such that the centers of positive and negative electric charge, this is the electron cloud, negatively charged, and this is the atomic nucleus, which is positively charged. And these two are equal, so that the atom or molecule is electrically neutral. So, to start with, the center of this negative charge distribution coincides with the central positive atomic charge. Therefore, this negative and positive charges coincide, and therefore, there is no dipole moment to start with. But when you apply an electric field, say along this direction, then the electronic cloud moves away. So, this is the way the electronic cloud is displaced in this direction from the original position. We assume that it is a rigid displacement without any distortion, so that this moves like this, and the positive nucleus moves a little bit. This is the nuclear charge. So, this is displaced to a much smaller extent because the nucleus is much more massive, therefore, it gets displaced to a much smaller extent, but still what is happening is the center of the negative charge and the positive charge here, there is a relative displacement. And this is what gives you a net dipole moment, which is induced and is present only as long as the electric field is existing. The moment you remove the electric field, this dipole moment will also vanish, because everything will relax back to the original situation. So, this is really the induced dipole moment. So, this is the mechanism of polarization. So, what really happens is that you have in a macroscopic dielectric, you have the positive charges going in one way and the negative charges going in another way in the presence of an applied electric field. So, this is what gives you a net electric polarization, but because of this displacement, there is also an electric field due to the presence of the positive and negative charges here. So, that gives you an internal electric field which depolarizes the original field, because it is acting in the opposite direction from the positive to the negative charge. So, this is the direction of the depolarizing field. So, the macroscopic electric field due to the applied field and the depolarizing field due to the charges which have been produced on the surface of the dielectric, that gives you a net macroscopic electric field, which is the sum of the E applied vector sum and the depolarizing field. but in addition to that there is an interaction among the dipoles, as I told you, which produces another contribution to this internal local field. Now, this therefore, let us call it E naught. Since this is opposing the applied field, let us call it E 1. If you have an ellipsoidal specimen, if your dielectric is in the shape of an ellipsoid, this depolarizing field can be shown to vanish. But in all other geometries, when the specimen shape is different from an ellipsoid, then the depolarizing field does not vanish, but even when it is not 0, it can be determined for standard geometries such as a spherical specimen or a long thin rod and so on. So, we can find the depolarizing field and add it vectorially to the applied electric field to obtain the macroscopic electric field. So, this is the first part. The second part is due to the dipoles which are in the immediate neighborhood of, suppose you have a dielectric and you have a given atomic dipole somewhere here, it's in its immediate neighborhood there are other dipoles. So, these are all different dipoles. So, these dipoles interact with this dipole and therefore, we have dipole-dipole interactions which produce an internal electric field. This situation can be considered quantitatively by considering a spherical cavity. We assume that we scoop out of the dielectric material mentally, of course, a spherical plug, and therefore, now you have charges on the surface of this cavity. So, these charges on the surface will produce an electric field, and then you have scooped out this material, but it is within this cavity there are dipoles. So, these produce an internal electric field. This electric field is known as the Lorentz field. Who calculated its value, and it can be shown that this field is E internal is P by 3 epsilon naught for a sphere. And then this is due to the surface charge, and in addition this field due to the charges in the spherical cavity can be shown to be 0 for a cubic material. So, we have all these various contributions, and the macroscopic electric field E local, the local electric field is E macroscopic P by 3 epsilon naught. So, it is this local electric field which is seen by the atom or molecule, the dipole, and therefore, this is what we have to write here. So, the individual dipole is now dipole moment is epsilon naught alpha E local, where E local is given by this. Therefore, correspondingly P also will change accordingly. So, P is n alpha E local. So, let us substitute this value of P and see what we get. So, we will get D is epsilon naught epsilon r E applied and this is equal to epsilon naught E plus P. So, this will give me a relation. P will be now epsilon naught n alpha into E local, which is E macroscopic plus P by 3 epsilon naught. So, collecting the P terms, there is a together we get P times 1 minus epsilon naught n alpha by 3, epsilon naught cancels, equals epsilon naught n alpha E macroscopic. So, because of this we get a modification in the Clausius relation between the relative dielectric constant or the susceptibility and the susceptibility. Therefore, we can show straightforward to show that epsilon r minus 1 by epsilon r plus 2 equals n alpha by 3. This is the relation which replaces the Clausius relation for a gas in the case of a solid or liquid dielectric. This relation is known as the Clausius Mosoti equation. So, the presence of the internal electric field produces this term in the denominator. That is how this is changed. And since the relative dielectric constant is proportional to the square of the refractive index, therefore, we can also write this relation, the Clausius-Mosoti relation, in this form. Where n is the refractive index. Say at optical frequencies. So, in this form, this is known as the Lorentz equation. So, these are the basic equations which govern the relative dielectric constant and the refractive index in the case of condensed matter. In the case of solids, so this is the situation. So, for example, if you take a material like sodium chloride, common salt. So, this has a refractive index n, which is 1.5, whereas this low frequency dielectric constant or static dielectric constant is 5.5, 5.6. So, if you square the refractive index n square, it is only 2.25. So, in going from a low frequency to a higher frequency, the value of the dielectric constant has come down, whereas in the case of a material like diamond, in which the bonds are stronger, therefore, the low frequency dielectric constant low frequency dielectric constant is 5.68. The refractive index at optical frequencies is 2.38. So, n square is almost close to the epsilon. So, there is not so much difference, n square is 5.66. So, you can see that in the case of diamond, the polarization mechanism is entirely electronic. The electrons contribute to the polarization, whereas in the case of sodium chloride, you have sodium ions and chlorine ions forming alternatively occupying a cubic lattice. So, these ions also have dipole moments. So, there is an ionic polarization in addition to the electronic polarization only. We saw already how the electrons start to give rise to a net dipole moment. That is the electronic polarization mechanism. So, we have two different polarization mechanisms, one of electron due to the displacement of the electronic cloud, and the other is due to the displacement of the positive and negative ions as in alkali halide. So, when both are simultaneously present, then the ions being massive are not able to follow the frequency variations at high frequencies. Therefore, the ionic polarization drops out, decreases as the frequency increase. So, at high frequencies the electronic contribution alone remains, whereas at low frequencies both the ionic and electronic contributions give rise to a large dielectric constant, static dielectric constant. In the case of diamond, it is exclusively electronic polarization. There are no ions there, it is a covalent solid, covalent bonds in the case of diamond, whereas here these are ionic bonds. So, when there are covalent bonds, it is only the electronic polarization which contributes to the polarization, dielectric polarization, and hence the dielectric constant. When you consider a material like water, water has, in addition to these, the water molecule has a very large dipole moment, ordinary water. So, it has an oxygen and two hydrogens. So, this is the structure of the water molecule. So, the OHO bond angle is approximately tetrahedral, something like 106 degrees or so approximately. So, this has a net permanent dipole moment. It is because you have the positive and negative charges do not coincide, and therefore, there is a net dipole moment even in the absence of an electric dipole, electric field, unlike the case of the spherical atoms which we saw in the case of the electronic cloud. So, this is known as a polar molecule, polar dielectric, which has an inherent non-vanishing dipole moment, and these dipoles due to the water molecules tend to reorient themselves in an applied field. So, reorientation in an applied electric field. So, this gives you, in addition to the ionic and electronic contribution, this gives us an additional orientational contribution to the polarization and hence the susceptibility and the dielectric constant. So, you have in all 3 contributions arising from different mechanisms to the net dielectric polarization and hence the dielectric constant. What are they? The polarization, electric polarization due to 1 an electronic polarization, 2 an ionic contribution, and 3 an orientational contribution. In general, all 3 will be present, for example, in the case of the water molecule. But when there are no permanent dipole moments, the electric field induces only electronic and ionic contributions. The ionic contribution is there only when there are ions which get displaced and therefore give you a polarization. Otherwise, when there are no ions in a structure like that of diamond, the polarization mechanism is completely electronic. So, these are, even among dielectrics, there are different kinds of dielectrics, and since the electrons respond rapidly to even very rapid frequency variations of the applied electric field, the electronic contribution continues, persists up to very high frequencies of the applied electric field. Whereas, the ions being more massive, they are unable to follow the rapid field variations above a certain frequency. Therefore, these ionic contributions are present only at relatively low frequencies. Similarly, the orientation of the permanent dipoles again happen at a relatively lower frequencies of the applied electric field. So, the electronic contribution is usually in the ultraviolet range, ultraviolet frequencies. The ionic contributions are in the infrared range, and this is the orientational contribution occurs in the microwave frequencies. So, as you change the frequency of the applied electric field and go through microwave, infrared and ultraviolet ranges of frequencies, these various contributions will give rise to polarization and hence contribute to the dielectric constant. So, the dielectric constant is frequency dependent. And it is this frequency dependence which give rise to a frequency dependent refractive index, because epsilon is just proportional to n square, and therefore, the refractive index determines the phase velocity of the electromagnetic wave in any given dielectric medium. Therefore, you can see that the phase velocity changes, and this is what we know as dispersion. So, the phenomenon of dispersion gives rise to arises from the frequency dependence of the dielectric constant. Now, let us consider this electronic polarization mechanism in a little detail. When we already saw that the electrons in a dielectric material are bound to the parent atoms and molecules and are displaced by the electric field. So, In the static limit, when the electric field is a static electric field, the atomic polarizability can be calculated using Gauss theorem. So, we assume a spherical atom and we apply Gauss theorem which is well known in electrostatics. So, if we consider Gauss theorem, we can write E of r for a spherical atom, the electric field is radially directed. That is why I am writing times 4 pi x cube, where x is the relative displacement between the electron and the nuclear charges. Therefore, this will be the electric field, and this is Gauss theorem giving you the flux due to the electric field, and this is given by the charge divided by epsilon naught. Now, if the charge, electronic charge, is distributed over an atom of radius a is the radius of the atom, then the electronic charge is smeared over a volume 4/3 pi a cube, of which we want to calculate the fraction of this charge intercepted by a spherical region of radius x. Therefore, this will be 4/3 pi x cube. Therefore, that is how you get the 4/3 pi cancels, leaving you with this fraction. This is the fraction of the electronic charge which is enclosed, and therefore, this gives me the Ex as E times epsilon naught into 4 pi a cube with a minus sign, in order to show that the dipole moment has a negative sign, the charge is negative. So, the dipole moment, this is the induced dipole moment. So, this gives me, comparing it with epsilon naught alpha E, where alpha is the polarizability, we arrive at the polarizability as 4 pi a cube. So, the polarizability of the atom, a spherical atom, is simply 4 pi times the cube of the atomic radius. The polarizability is proportional to the atomic volume. Let us now consider, we will consider in the next discussion, what happens when we go from a static field to a frequency dependent field, an applied alternating field. We will consider this in the next lecture.